Hello again for another digital replay. Today we're concentrating on what are the ice ages. And those are on pages 609 to 625 in the orange textbook. So let's see. The last ice age, or the last glacial maximum, or LGM, started about 70,000 years ago and ended about 10,000 years ago. And this was during the Pleistocene. And the Earth was much colder than it is now, and snow accumulated over much of the land. Glaciers and ice sheets extended over large areas, and the sea levels were much lower. Here, this little black line indicates the level of the ocean. So everything inside of the black line would have been land. So you see that the land would have been much larger. We would have had much bigger continents at that time. The phenomena, like the ice sheets, were changing the surface of the earth. They were carving it out, forming lakes, changing the paths of rivers, eroding the land, depositing sand, huge boulders, gravel, all along the glacier's path. So an ice age is a cold period marked by extensive glaciation. That's what an ice age is. It's a cold time in the climate, and there's a lot of ice during that time. So if we were looking at a map of the United States, the ice sheet would have covered much of Canada. See, the ice sheet here would have covered all the way down here into the northern United States. And this isn't a completely accurate picture. This is just going to be an estimation here. This is what it looks like when you're covered in an ice sheet. Wow, look at that land. Look at all of those amazing mountains. So here's a more accurate picture of what the Laurentide ice sheet and what it looked like, and the Cordilleran ice sheet. And notice that here's a little blip right up here. Guess where we are in Ellensburg? Oh, we're right there. And then so here's the fingers of the ice sheet coming down here.
Here are just a few of the places in North America where evidence of glaciation can be seen. Clearly, glacial ice once covered this much of the land and extended an unknown distance out to sea. Today, glacial ice covers only these areas, so it is obvious that the ice melted back at least once.
Kansas would have looked like this. So this would have been Kansas. And the reason that this land is so fertile is because it's fed by those glaciers. All that carving of the rocks, all that, and would wash down. Some of that till would wash down and get to the fertile plains of the United States. And that's what makes the fertile plains so fertile, was from these ice ages. Isn't that crazy? If we look at other formations in the United States, like Cape Cod, Massachusetts, this formation here is because of the carving of the glaciation, the carving of the ice. Long Island, this was formed by glaciers as well, carving of the ice. Now, here we have a little animation about glacial and interglacial periods. So during an interglacial period, we have high sea levels, we have evaporation, and during a glacial period, we have lots of accumulation of ice. And notice that when the water is not in the ocean, it's locked up in ice, so the ocean level is much lower. So the sea level was much lower during the glacial periods because the Earth's water from the oceans was trapped in the ice. So that's not during the interglacial, that's during the glacial period. So when the sea level is lower, we have more land expanding out into the sea here. So our continents are much larger. And what you notice is we actually form these land bridges, so to speak, between two areas that right now do not have a way to get between one and the other. This is really cool. This is how early humans may have gotten to the United States, what is now North America, by a land bridge over there by Alaska. Perhaps they just walked across, because this would have all been land. So how on earth could we possibly know that these ice ages happened? I wasn't there. Were you there? How could we know? Well, the first thing you need to understand is the difference between weather and climate. Climate is weather over a long period of time, and usually over a big expanse of area. Okay, so weather over a long period of time. Well, weather is what's happening today or in the short term, maybe days to a couple of weeks. And it's a certain place. Climate, this is going to be a large, expansive place. But weather, this is a certain time and place. This is talking mostly about the clouds, the precipitation, the humidity, the temperature, the wind. That's what is weather. If the climate is cooler, the climate is cooler over long periods of time, ice can build up. Do you remember the animation from the last video of glaciation, how to make glaciers? And in the wintertime, you have snow and you have accumulation. In the spring and summer, you have a little bit of melt off, but a lot of snow and ice stay in the mountains. And because it stays through to the fall, you have an accumulation time. You have more time to build up more snow. So the cooler summers, the cooler springs and the cooler summers allow for that ice and snow to stay, and that makes more buildup of ice and snow over the winter and fall. More ice locked up in ice sheets and glaciers, that means less water available in the oceans and rivers and streams. This is all tied back to the water cycle, right? So here we have our water cycle, and what we have is we have to have some evaporation happening, the evaporation from the oceans, lakes, and streams, which eventually will condensate on the mountains, making there be more snow in the mountains to accumulate all of that snow and ice that happens during a glaciation. Okay, now snow, ice, water, it's all made out of H2O, two hydrogens and an oxygen. Here's oxygen's thing on the periodic table. And you notice that it has an atomic number of 8, which means that it has 8 protons and usually has 8 neutrons. Now, every once in a while, you get an oxygen atom that has more neutrons or less neutrons. We call these isotopes. So if you have an oxygen with more neutrons, let's say it has 10 neutrons instead, we're going to call that oxygen 18. And the reason we call it oxygen 18 is because it has 18 things here inside of its nucleus. It's got 10 neutrons and 8 protons. Usually, like I said, it has 8 protons and 8 neutrons. So usually it's oxygen 16. But every once in a while, you get some that have more, like oxygen 18, and you do get some that have less. You always have 8 protons, but the number of neutrons can change. Now, if you have more neutrons, you have a heavier atom. That atom has more mass. So if it's a heavier atom, what happens is that the water itself becomes heavier, and heavier water doesn't evaporate as much. It evaporates much more slowly. So you're going to get more evaporation of the oxygen 16 and less evaporation of the oxygen 18. So if your oxygen 16 evaporates and then precipitates onto the mountains, then gets locked up in the snow and ice, your concentration of oxygen 18 in the oceans is going to increase. So if you have a higher concentration of oxygen 18 in the oceans, these little organisms called foraminifera can take that oxygen and they're going to put it into their shells. No matter what the oxygen is, 16, 18, whatever it is, they're going to take that oxygen and they're going to incorporate it into their shells. Now, if there is more oxygen 18, then the higher percentage of the oxygen in the little foraminifera shells is going to be oxygen 18. Those shells die, or those organisms die. The shells themselves don't die, but the organism inside the shell dies, and they sink to the bottom of the ocean. And when they're there down at the bottom of the ocean, they eventually get buried over long, long periods of time by other dead organisms, right? And what we can do is we can actually drill a core, is what it's called, C-O-R-E, core. We can drill a core of this ocean sediment, and we can take that core out and study each of the layers of that core. In each of the layers, we're going to find those little foraminifera, the little teeny shells. And when we look at what are those shells made of, we can see what percentage of the shell is made up of oxygen 18 and what percentage is made up of oxygen 16. And knowing what we know about the evaporation rates of oxygen 18, we know that at times where oxygen 16 is locked up in ice, we're going to see more oxygen 18 in the shells. So here we have more oxygen 18 in the shell. That tells us that there is more oxygen 16 locked up in ice, not going through the water cycle. And so that oxygen 16 absence, or the increase in oxygen 18, tells us that this period up here was an ice age, or it was a colder climate, because more of the oxygen 16 is locked up in ice. This is really, really cool, and it takes a lot of steps to understand this. So I'm trying to go through it several different ways. But here we can see more oxygen 18 in the foraminiferous shells, and here we can see less oxygen 18 in the foraminiferous shells. So less oxygen 18, more oxygen 16. Oxygen 16 is going through the water cycle very easily. It's not being locked up in ice. It rains down, it melts, it comes back to the ocean, so we have more of it available to be incorporated into our shells. Up here, we've got less oxygen 16 being used, more oxygen 18 being used, and the concentration of the oxygen 18 tells us that, yes, indeed, we are in a ice age, or a cooler climate.
Isotopes are atoms of the same element with different numbers of neutrons. Oxygen 18 has 2 more neutrons than oxygen 16, therefore it is heavier. Because oxygen 16 is lighter, more of it is evaporated out of the oceans, while greater amounts of oxygen 18 stay behind. This is called fractionation.
As our weather systems move northward and across continents, more of the heavier isotope oxygen 18 is precipitated out of the clouds, leaving a higher ratio of the lighter isotope oxygen 16. This means that as these weather systems get closer to the poles, they are holding far more oxygen 16 than oxygen 18. Once the clouds reach the poles, they dump the remaining oxygen isotopes in the form of snow.
More oxygen 16 is falling because, remember, there is a much higher ratio of oxygen 16 than oxygen 18 in the clouds. This explains why glaciers have greater amounts of oxygen 16 than oxygen 18.
Forum is a small ocean creature that holds oxygen within its shells. Fossils of these forams can be discovered in ocean sediments. When the shells are studied, scientists can determine which oxygen isotopes were most abundant during the foram's lifetime.
If the foram has more oxygen 16 in its shell, we know that it lived during a warmer period with less glaciation. If the foram has more oxygen 18 in its shell, it lived during a cold period with more glaciation.
So let's sum that up really quick. More oxygen 18, that means oxygen 16 is trapped in the ice. Less oxygen 18, that means that the oxygen 16 is freely cycling and able to be incorporated into the shells. Whoa, crazy. Now speaking of cores, we can also take core samples of lake beds. And what will that tell us? Well, we look at the mud inside of the lake beds and look at all those beautiful layers inside of the mud. Each of those different layers represents a different time period throughout the lake's history. And what we can do is we can look inside of those mud samples, each of those different layers of mud, and we can look for pollen. Because if we can identify the pollens, we can use the growing conditions of those plants to tell us more about the climate during that time. And we did a lab doing just that. That was really cool, but now we're out of time. So during the Ice Ages, large sheets of ice covered the Earth. Sea level was much lower. We know this because we can drill ocean sediment cores and look at the oxygen 18 concentrations. We can also look at pollen data, and there's so much more, but we don't have time for it today. Thanks for watching Digital Replay. If you have questions, comment below, send me an email, or see me in class. We'll see you next time.